Hi, my name is Dana Van Aken, and today I'm going to be presenting our paper, An Inquiry into Machine Learning-Based Automatic Configuration Tuning Services on Real-World Database Management Systems, which is a collaborative effort between the Carnegie Mellon Database Group, Princeton University, Societe Generale, and OtterTune. Modern database management systems expose dozens or even hundreds of configurable knobs that control all aspects of their runtime behavior, such as the amount of memory to use for caches or how often data is written to storage. Tuning these knobs for the workload and hardware is essential for data-intensive applications because the difference in performance between good and bad settings can be substantial. But because of their complexity, tuning a DBMS often requires the expertise of an experienced database administrator. Given this, there have been several efforts to automate configuration tuning since the early 2000s. The first of these were mostly proprietary tools that configured a limited number of knobs using heuristics that were based on the knowledge of experts. More recently, several machine learning-based methods have been proposed, including our work on OtterTune in 2017, and the evaluations showed that ML-based tuners can achieve better performance compared to DBAs and other tuning tools. The reason is that ML-based tools can consider more knobs than heuristic-based tools, and they can handle dependencies between knobs that are difficult for humans to reason about. However, the evaluations of ML-based tuning tools are limited, and some aspects are inconsistent with real-world deployments. In particular, the three mismatches, or aspects, that are inconsistent with real-world deployments are that these studies only consider open-source database systems in synthetic benchmarks, and they run their experiments on dedicated local storage. I will now discuss each of these further. The first mismatch is that previous works only consider open-source DBMSs with limited tuning potential. To demonstrate this, we've plotted the throughput for the TPC-C workload for 4 different configurations across 3 different versions of MySQL and Postgres. The orange bar shows the performance from tuning 2 configuration knobs that control the size of the buffer pool and Redolog file, and the black and green bars show the performance achieved by 2 ML-based tuners that each tune around 10 knobs. The number on top of the bars is the % improvement of the ML-based configurations over the 2-knob configuration. The takeaway is that for the TPC-C workload, you can achieve at least 75% of the improvement you get from the optimized configurations by tuning only 2 knobs across these MySQL and Postgres versions. But what we wish to know is, how do commercial systems compare? The second mismatch is the workload. This graph shows the query type distribution for an enterprise workload versus the TPC-C benchmark. We see that the TPC-C benchmark has a much higher write ratio than the enterprise workload, and this finding is consistent with comparisons in past work. There are other differences too. For example, with the schema, in production workloads, some tables have hundreds of columns and dozens of indexes. Overall, there are aspects of TPC-C that are not representative of production workloads. The third mismatch is the operating environment. Even though these evaluations use virtualized environments, like the cloud, to the best of our knowledge, they all use dedicated local storage to the DBMS, like SSDs attached to the VM. But many real-world DBMS deployments use non-local shared storage for data and logs. This graph shows the I/O latency for a random read workload on both local and non-local storage. In addition to incurring higher latency, these non-local storage devices also have much more variance in their performance, and it's unclear how these differences affect the efficacy of ML-based tuning algorithms. Given this, we were very excited when we were presented with the opportunity to do a field study with Societe Generale, the 3rd largest bank in France, to better understand how well ML-based algorithms perform when tuning on a commercial DBMS and a real-world workload. For this study, we extended the OtterTune configuration tuning service to support other state-of-the-art algorithms, which I will describe next. In this study, we compare the efficacy of 4 tuning algorithms. Here I give a high-level description of each algorithm, but please see our paper for more details. The first is GPR. This is an ML-based tuning algorithm proposed in the first OtterTune paper from Sigmod 2017. It uses a pipeline model and at its core uses Gaussian process regression to make configuration recommendations. For the second algorithm, we keep the same ML pipeline but replace the GPR model with the deep neural network. OtterTune adds Gaussian noise to the parameters of the neural net during the knob recommendation step, which can be adjusted to control the amount of exploration versus exploitation. DDPG is an actor-critic algorithm that aims to find the optimal policy in an environment with a continuous action space. We implement the algorithm used in the CDB-Tune paper, which is a traditional version of this algorithm. Finally, LHS is a sampling technique, not an ML-based technique, that is smarter than random sampling. We use it as a baseline in our experiments. The DBMS version we used in our experiments is Oracle 12.2c. For this study, we cloned a 1 terabyte production database and captured a 10-minute workload trace, which we replayed using Oracle's Real Application Testing Toolkit. The production workload in our experiments is an internal application to track the assignment status and progress of tickets submitted to tech support. We refer to it as the ticket tracker workload. Lastly, the target objective that we tune for in our experiments is an Oracle-specific metric called the DB time, which measures the total time spent in database calls by foreground sessions. I will now share some of the results from our evaluation. This first result demonstrates an unexpected challenge that we encountered during this study, which was a high variation in performance across the VMs we used in our experiments due to latency spikes in the shared disk storage. This graph shows the DB time for the ticket tracker workload when running with the default configuration across our VMs over a 6-week period. The results show how the performance varies widely across the VMs during the same time period. They also show how the performance can vary greatly for the same VM over time. This meant that we had to conduct many trials per experiment in order to reliably compare the results, and this was a time-consuming process since each trial took around 3 days to run. I will now share one of our main results from the paper. In this experiment, we compare the efficacy of the 4 tuning algorithms when tuning 10, 20, and 40 knobs. The list of knobs tuned was selected by the DBA based on those they believed to be the most important. We plot the percent improvement in the DB time over the default configuration. Note that some of the knobs in the default configuration had already been tuned, including the size of the buffer pool. The results show that there is no major difference in the quality of tuning among the 3 ML-based algorithms. They're all able to beat human tuning. GPR converges the fastest, but DNN has slightly better results. DDPG would likely perform better if we ran it for longer, but due to time constraints, we couldn't do this. Although LHS is a competitive baseline for 10 and 20 knobs, its tuning sessions took much longer to run than the ML-based techniques, since inevitably it picks poorer performing configurations more often. Overall, DNN performs the best, but all the ML-based algorithms were able to improve performance by at least 30% over the default configuration. For the remainder of this talk, I'm going to discuss some of the important lessons we learned while conducting this study. Foremost is that there were unexpected cost considerations. Although the performance gains achieved by the ML algorithms are noteworthy, there was a trade-off between how long it took to deploy OtterTune versus the benefit. For example, cloning the production database and capturing the workload trace took over 2 months due to scheduling and requesting permissions and resources. There are several non-obvious factors one must consider, like the economic significance of the applications an organization wishes to tune, and the tooling and infrastructure available to run the tuning sessions. We also learned that the tuning data we collected was not a privacy concern. The bank was able to share the knob and metric data with us, even in light of GDPR restrictions. We had other learnings too, such as handling bad configurations that I will describe now in more detail. When there is little prior training data, such as at the start of a tuning session, the tuning algorithms will choose bad configurations that can cause failures. There are 2 failure scenarios. The first is that the DBMS refuses to start because the knob settings are invalid. The second is that the DBMS will start but then crashes at some point during the workload replay. For Oracle, this can happen if the buffer pool size is set too large since it allocates this memory incrementally. When this happens, it is important to indicate these failures to the ML algorithms so that they learn that this was a bad configuration. But we must decide what metrics to use for training the ML algorithms, since the metrics from a delayed crash may not be scaled correctly, and thus the algorithms could incorrectly learn that a bad configuration improved the target objective. Our solution is to return the metrics from the poorest, and that brings us to the And that brings us to the end of this talk. Thank you for attending, and please reach out with any questions.